good day, everybody. And once again, we are back together. This time, we'll be looking at physical science, grade 11. All right, so please, if you haven't subscribed, just make sure that you're part of the family. And of course, your uncle will continue to give you good content in maths and science. For those of you that require assistance, please make sure that you go to the description of this video. All our contact details are there, and you can obviously pull through at our wonderful Mlungisi Nkosi Center, right? That is based in Hanichu, or you can either join us online as well. All right, so let's get right into this question paper and let's see what it has in store for us. So starting with the multiple choice sections, right? So they say which one of the following pairs of quantities, of physical quantities, is vector quantities. Now note, it means that both of them need to be vector quantities. Well, let's look at the first option, force and distance. Well, distance is not a vector quantity. Velocity and speed. Speed is not a vector quantity. Charge is not a vector quantity. And the last one, they say electrical field, it is a vector, as well as force. So in that case, our answer there should be D. Right, so let's go to the next one. They say which one of the following vector diagrams represent three vectors acting on an object simultaneously while the object moves at constant velocity. Now, ladies and gents, remember that constant velocity means that acceleration is 0, right? So, and that means that the forces must be at equilibrium. It means that the net force is also equal to 0, and so the forces are at equilibrium with one another. Now, please note, if they are at equilibrium with one another, then the triangular law of forces in equilibrium, right, says that those forces need to be drawn in such a way that they make a head to tail diagram, right? Okay, so if I look at that, the only head to tail diagram in this case, right, is A. So that means that that's the only diagram. Now note that on all the other diagram, you had two heads that were actually meeting at one point. So that means that that system would not be at equilibrium. Right, so let's go to the next question, guys. So they say a block of mass of 4 kilograms is pulled upwards along a frictionless slope. Note frictionless, inclined at an angle theta, right, with a force F as shown in the sketch diagram. Now note in this case, they say which one of the following equations can be used to calculate the magnitude of the normal force. Now remember, on an inclined plane, our normal force would be equal to the perpendicular component of gravity, right? And in this case, to get that component of gravity, we always say this is mg, the cosine of the angle of elevation, which is theta in this case. Right, so this is going to be mass times 9.8, the cos of theta. So our normal force there should be, all right, so it looks like D will be our answer. Right, and then the next one, they say to us a satellite orbits Earth at a height where the gravitational force is a quarter of the force it experiences on the surface of the Earth. Now, let's just say for argument's sake, here's Earth, right? So in this case, if we had placed the satellite there, it would experience a force F. Okay, so let's say that the radius from the radius of the Earth is R, right? So which means that the satellite would experience force F, right? Now note force F would simply be G, the mass of the Earth, the mass of the satellite, divided by R squared, right? Now, they say to us, if the radius of the Earth is R, this is what we just did there, they say the height of the satellite above the surface of the Earth is. Now note, what happened here? They said the gravitational force that it experiences at a certain height is now a quarter of the force. Now, the only way that we could have that force being a quarter, or being, in this case, 4 times less, right, is if what we did was the mass of the Earth and the mass of the satellite would be the same, right? And in this case, it means if we have 2 times the radius of the Earth, right? So you'd notice if we calculate this, we will get 1 over 4f, right? So we will get 1 over 4f. So which means that the satellite has to be a distance, another distance r away from the Earth. So the satellite needs to be here, right? So now, remember what was the question? They said the height of the satellite above the surface of the Earth is. So above the surface of the Earth, it is a distance r away. But from the center of the Earth, it is a distance 2r. But we are interested in above the Earth, so it is just a distance r. So our answer will be C. I hope that makes sense, guys. Right? So let's go to the next question. They say a light ray passes from glass to air, right? The angle of incidence is 35 degrees. They say the critical angle of glass is 38 degrees, right? Now note what will happen to the light ray. The light ray will undergo. Now notice this, we're going to be using Snell's law here, right? So what's going to happen, right? We have light that is incident. So at the end of the day, we know that it will refract, right? And it will bend away from the normal, right? So in this case, we're going to have B as our answer right there. Right, so the next question, they say the path of a light ray passing from air through a perpendicular perspex block is shown below. They say the magnitude of the angle theta will be. Now, once again, in this case, this is our incident angle, okay? Now, in this particular case, we know that we've got perspex, so the angle theta should actually be equal to 39 degrees, right? Please note there. So it should also be equal to 39 degrees, right? And I'll take some time to explain Snell's law, just so that you are able to understand it much better. Right, now the next question, they say a monochromatic red light passes through a single slit of width d. Right, they say the diffraction pattern is projected on a screen. The red light is then replaced with monochromatic blue light. Now note, what are we doing? We're taking light with a longer wavelength. We are substituting it with a light that has a shorter wavelength, right? And they say the degree of diffraction will. Now note that when we look at diffraction, we always say the sine of theta is m multiplied by the wavelength divided by a, which is the slit width, right? Now, I want you to note in this case, what is our what did we do to the wavelength? We substituted a light, or rather a light source with a longer wavelength to one with a shorter wavelength, right? So what will happen to the degree of diffraction in that case? Okay, so let's look at the answer. It says it will increase. No, there's no way that it will increase, so it should decrease. So the answer is between B and D. Let's see, decrease because blue light has a shorter wavelength than red light. Absolutely, that is true. Let's see why D wasn't the correct one. They say decrease because the degree of diffraction is inversely proportional to the wavelength. That's not true. The degree of diffraction is directly proportional to the wavelength. Right, so that's why B would be the correct answer. Right, now the next question, they say a negative charge of 1 microcoulomb, which is free to move, is placed at a distance 2r from a positive charge of 4 microcoulombs. They say which one of the following statements regarding the 1 microcoulomb charge when it is a distance r is correct. Okay, now obviously if I were to bring it closer, okay, what should happen? It means that the force between the two should be larger, right? So the force between the two will be a larger force. Okay, so now they say to us the electrostatic force experienced by the 1 microcoulomb charge will, okay, it should increase, right? Now note that you have halved the distance. So if I halve the distance, the force will actually increase 4 times. It will quadruple, right? So in this case, this is going to be increase 4 times. That is it. Now note, ladies and gents, that's K, Q, all right, let's call them Q1 and Q2. And what did I do? All I did was to make the distance half as much. Remember, our initial distance was 2r, right? Now it's r, so which means it's half the distance, right? Let me just say half d, okay, squared. And what happens? Because you've got half at the denominator, okay, that's Q2 divided by, this is now 1 over 4d squared. Now to get rid of this 4 in the denominator, I will multiply by the inverse. But what I do at the bottom, I do at the top. So that cancels with that. And you can see that the force becomes 4 times as much. And so we end up with 4 times, right? Okay, so the next question, they say a circular coil is placed inside a magnetic field and rotated clockwise to induce an EMF. Which one of the following changes will increase the induced EMF? Now, please remember that when we look at the induced EMF, okay, we say that that's minus n, that's the change in phi divided by the change in time. Now, remember, the only things that increase EMF, right, would be increasing the number of coil turnings, right? Increasing the magnetic field, either using a stronger magnet, okay, so that's magnetic field, okay, and in this case it would be this the rotation, the number of rotations, right? So if I look at those 3 things, those are what increases the EMF, right, as for Faraday's law. So they say to us we wanted to improve the EMF, right? So they said rotating the coil slower. That's definitely not true. Decreasing the number of turns, windings on the coil, not true again. Increase the speed of rotation, right? That definitely does look true there. If I increase the rotation speed, it will improve the EMF significantly. And then they said changing the polarity of the magnets. Definitely that will not do it because changing the polarity will just change the direction of the current. Okay, and finally, they say in the diagram below, the battery has negligible resistance. The resistance of the emitter and the wires may also be ignored. Right, now please note in this case, they say the reading on the voltmeter V3 will be equal to. So if I look at V3 there, so they wanted you to actually assume that V1 will actually be equal to V3, but that would not be true because remember, when current moves through this circuit, once we get to this node over here, right, what happens? The current will divide. So some of the current would go there, okay, and some of the current goes there. Now note that the current that goes through the 8 ohm also goes through the other 8 ohm resistor. So which means these 2 resistors must be in series with each other, right? And it is the combination of both resistors that is in parallel to the 4 ohm resistor, right? So in essence, what we actually have is the 4 ohm resistor there, and we've got 2 resistors over here, right, that are sitting, and these are the 8 ohm resistors respectively. Right, now what happens? It means the voltage on V1 will be equal to the voltage on both these resistors together, right? But what do these resistors do? They divide that voltage with each other, and since they are equal, they will divide it equally, so which means that the voltage V2, or rather V3, will be half of V1, okay, because they divided that. So in this case, they said the reading on V3, right, will be half of V1. All right, I hope that makes sense, ladies and gents, and you'd have earned yourself a good 20 marks. I hope that you would understand. All right, so now let's go on to the long questions in question 2. And question 2 says we've got block A, which is at rest on a rough, or rather horizontal rough surface, right, which is used as an anchor to hold block B. They say with a mass of 56 kilograms in the air at a certain height above the ground. The 2 blocks are connected with rope R, which makes an angle of 35 degrees with the vertical. They say block B is suspended from the ceiling with cable C. Refer to the diagram below. Right, now they say to us block A experiences frictional force of 200 newtons. The system is stationary. Now this is very important, right? So in this case, that means that all the forces must be at equilibrium with one another. So the vector sum of all the forces should be 0. Right, now they say to us define the term resultant vector. So remember that we know that it is the vector sum, right, or rather it is the sum of vectors, right, or we can say that it is a single vector that has the same effect as 2 or more vectors combined, right? Okay, the first definition, we know that it is the vector sum of 2 or more vectors, right? Okay, so they said to us, they say to us rather in the next one, what is the magnitude of the resultant force acting on block B? Right, so goes without saying, we know that the vector sum of those forces should be 0 newtons. Remember, because it is stationary, we said in this case it means that the total, or rather the vector sum of the forces should be 0. Okay, right, so let's go on to the next one. They say draw a labeled free body diagram indicating all forces acting on block B. Right, so I'm just going to draw it over here. Okay, I will have the force on rope R. Okay, force on R. And I'm going to have gravitational force in this case, or the weight of B. So that's weight over there. As well as, in this case, we've got, okay, so I didn't draw that very nicely there. Right, so we've got force C, the force on rope C. Right, and that is what our vector diagram looks like. Okay, so I hope that you got it, ladies and gents. Right, so those are the 3 forces that are acting on B. And by the way, please remember that the mark allocation would tell you how many forces you need to have on that diagram. Right, so they said determine the horizontal component of the force in rope R. Right, now note, ladies and gents, what do we note about this block here? We know that it is experiencing friction of 200 newtons, isn't it? And we know that that friction, in this case, what is pulling this guy in that direction? It would be the component of that force on the rope R, right? So the force, the horizontal component on the force on R, in this case, should be equal to that frictional force, which is 200. So I am, because that's 1 mark, so it means that the horizontal component should be equal to 200 newtons. Right, so let's go to the next one. They say calculate the vertical component of the force in cable C. Okay, ladies and gents, now let's go to this diagram now. So I already know that I've got a horizontal component here, right, of the rope on R being 200 newtons. And I know that the horizontal component of the force on C, right, should also be the same, isn't it? Because those are the only two forces that are acting horizontally there, right? But they are not looking for the horizontal component, they are looking for the vertical component of that force, right? So in this case, I know I am looking for this guy over here, right? So I'm just simply going to say, right, so I'm looking for the vertical component on C, right? So now if I look at this, that means that if I take the alternating, alternating angles, that should be theta as well, right? But what else do we know as well? We know that the horizontal component of that force should also be 200 newtons, okay? Right, and in that case, we can actually find out what the vertical component should be. Right, now please, I want you to note, ladies and gents, we also do not have, in this case, we don't have the angle theta. We're not given that, that angle of theta there. Right, now let's start, okay? So we're looking for the vertical component, right? So what I'm going to do is, let's start firstly, right? I know that the force on B, the weight of the block there, so that weight is mass times gravitational acceleration, right? So this is going to be the weight. So if I look at the forces that are acting, or let me rather say the vertical forces that are acting on B, right? So that would be, it would be the vertical component on rope C. It would be the vertical component, okay, on rope R, but it would also be the weight of that block. Okay, right, so I'm looking for the vertical component of on C, right? So let's actually try to calculate it there. Right. Okay, I'm a little bit out of space. Okay, let's write at the bottom there. So I'm going to say the vertical component of C plus the vertical component on R minus the weight, and this is equal to 0, right? The vector sum of all those forces, right, vertically should be equal to 0. So I'm looking for this guy here, right? So that would be the weight on B minus the vertical component on R. Now, ladies and gents, this is going to be, the mass of B is 56 times 9.8. Now, let's talk about the vertical component of R, right? So we're looking for this guy over here. Okay, now note, what do we notice? We had the angle of 35 degrees, and we knew what is the force, the horizontal component of that. We know it is 200 newtons, but I'm looking for the vertical component. So which angle am I going to use? Well, the tan of 35 would be opposite over adjacent, because I'm looking for this guy over here, the vertical component, right? So notice, so tan of 35 would be opposite, which is 200, divided by adjacent, which is the vertical component, right? So for me to look for the vertical component, it means that it will be, so F vertical will be 200 divided by the tan of 35. So I want you guys to please note in this case, what am I doing? I'm treating this guy as a 90-degree angle, triangle, right? I am looking for, let me just show you there. I knew that this side here was 200 newtons. That's what we said the horizontal component is, right? So now, because I'm looking for the vertical component, right, so we then used the tan, which is opposite, over the adjacent side, which is this vertical component. And so as a result, that's how we got to that. Okay, so that means this angle here, F vertical, or rather the side, would be 200 divided by the tan of 35. Okay, and let's find out what that is. So that's 56 times 9.8 minus 200 over the tan of 35. All right, ladies and gents, and what I get there is 263.17 newtons. I hope that makes sense, guys, right? That is how I get the vertical component of that angle there. Right, now let's go on to the very last question. They say calculate the angle theta between the cable and the ceiling. Now, what I'm going to do, ladies and gents, let's do this. Let me go to rope C. Okay, and there is a sketch of rope C as well as the components on rope C. We already have found out that this guy is equal to the horizontal component on the rope R, so which means that's 200 over there. We found out that the vertical component was 263.17. So now what do we note? Which means this angle here, notice that I've drawn the line here parallel to that one over there, right? So which means we've got alternating angles, so that means that is theta. So what do we have? We've got the opposite side, we've got the adjacent side. So which means to get 2.6, all I'm going to say is tan of theta will be opposite, right? The opposite, it's the vertical component. That's 263.17 divided by the horizontal component, which is 200. And so theta will be equal to the arc tan of 263.17 divided by 200. Okay, and let's find that angle there. Actually, let me just say shift 10 of 263.17 divided by 200. And I get an angle of 52.77. Okay, and that would be our angle theta. Right, so please keep in mind, ladies and gents, that because we had a system that is in equilibrium, that is essentially how we are going to calculate that. That would be out of 13 marks, and so that is how we come to the conclusion of question 2. Let's go on to the next one. All right, now let's look at question 3. They said learners investigate the relationship between net force and acceleration by building a trolley across a surface which is slightly inclined to compensate for friction. They say the trolley is connected to different masses by a string of negligible mass. The string passes over a frictionless pulley. They say refer to the diagram below. Right, so there's our ticker timer there, and we've got the different masses and so on. So they say ticker tape attached to the trolley passes through the ticker timer. The acceleration of the trolley is determined by analyzing the ticker tape. The result of the net force produced by the different masses and the acceleration of the trolley were recorded in the table below. Right, so there it is. They give us the data there. All right, and so I think just looking at this data, it seems to suggest that every time that we are increasing the net force, we seem to be increasing the acceleration as well. I hope that you can see that. Now they say to us, write down a hypothesis for this reaction. Now remember, a hypothesis would be a calculated guess, right? Okay, of what the results would be. But I mean, we already have the data right in front of us. So what would be a suitable hypothesis? We would essentially just say, as the net force increases, right, the acceleration also will increase. Or you can say that acceleration is directly proportional to the net force. That is also a suitable hypothesis. Right. Now they say identify the independent variable. Now remember, ladies and gents, what would be the independent variable? The independent variable is always what you are changing, right? So what is it that you are physically manipulating in your data, right? It is the mass, and as a result, the net force that is acting on this guy. So I would say that our independent variable would definitely be the net force, right? Okay, we keep tampering with the net force, right? As we keep changing that mass, it changes the net force, and as a result, what would be our control variable? So acceleration would be the dependent variable. Remember, acceleration depends on the net force, right? As you keep changing net force, acceleration changes. So that would be your dependent variable. But what do we keep constant in this particular, I would say the mass of the trolley, isn't it? So I would say definitely it would be the mass of the trolley. Okay, right. We are changing the mass there, but that does not change the mass of the trolley, right? So the reason we are changing this mass is so that we can have a different pulling force here, right? So that it affects the net force. Right, and then now they say to us, use the graph paper on the answer sheet and draw a graph of the acceleration versus net force. Right, now, ladies and gents, we are provided, just take a mental picture of these values. I've taken them, and what I'll do is I'm going to try and draw that graph right at the bottom there. Right, so let's go right to the bottom. There we are given our graph. So you remember we had our values, right? In terms of net force, we've got 0.3, 0.6, 0.9, and 1.2. Right, so we've got all of those forces over there, right? So what I'm going to do is we need to choose a scale. But when you choose a scale, for instance, if I were to say 0 0.3, 0 0.6, 0 0.9, and 1.2, can you see that my graph will only fill only half of the half the entire graph that I'm given, or half the space that I'm given. And the rule is your graph should always be greater than half of the space that is given there. So let's choose a different scale. So what I'm going to do is let me choose 0 0.2. So I'm going to have 0 0.2, 0 0.4, 0 0.6, 0 0.8, 1.0. Can you see now I went beyond just half, right? So that would be 1.2. Okay, let's say 1.4 and continue from there. Right, now, equally so when you look at your force values, rather your acceleration values. So your values are 0 0.36, 0 0.7673 up until 1.45. Okay, so I think just to make it easy as well, I'm going to choose 0 0.2 as well as a scale there. 0 0.2, 0 0.4. Okay, I can't see those lines properly now. 0.6, 0 0.8, that's 1, that's 1.2, that's 1.4, 1.6, and 1.8. Right, so we know we're only going up until 1.45, which should be somewhere over there. All right, now ladies and gents, let's start with the first value. Our first value is 0 0.3 and 0 0.36. Okay, so let me just take out my ruler here. Right, now 0 0.3, right, apologies there. So we've got 0 0.2, which means halfway between 0 0.2 and 0 0.4 is 0 0.3, right? So there we go, way over there. So here is our 0 0.3 mark, and our corresponding y value is 0 0.36. Okay, so 0 0.3. Okay, let's just make our ruler 90 degrees, because then it skews our value. Okay, so there we go. So I'm going to have 0 0.3, which is this line over here, and 0 0.36. Now note, so which means my graph, that's 0 0.2, that's 2, 4, 6, 8, 10. This would be 0 0.3 over here, right? So 2, 3, 2, 3, 4, and 3, 6. Okay, I seem to have something that looks a little bit amiss there. Okay, so that's 0 0.2, that's 2, 4, 6, 8, 10. So that's 0 0.3, 0 0.32, 3, 4, and 3, 6. So that should be that value here. All right. So there it is over there. The second value, right, is 0 0.6 and 0 0.73. So 0 0.6 is quite easy. It's that value there. Now let's find 0 0.73. Okay, so let's take out our ruler again. So 0 0.7. Okay, so 0 0.7 is really above 0 0.6. Okay, so that's 2, 4, 6, 8, 10. So that's 0 0.7 over there. Now note, we want 0 0.73. So this would be 0 0.72. So right in the middle there, you've got 0.73. So this should be the value over here. Right, and our next value is 0.9 and 1.09. So 0.9, again, it's midway between those two values, and 1.09. Okay, so 1.09, so that's 1. So 1.1 should be somewhere there. Okay, so that's 2468, 1.08 and 1.09. Okay, so we should be somewhere here. Right, so that's our third value. Okay, and then finally, okay, I'm taking my time so that I show you how to plot these. So 1.2 and 1.45. Okay, so 1.2, that's easy, right? It is this line here. And 1.45, so that's 1.4, that's 2, that's 4, and that is 6 there. Okay, 1.452, that's 4. So it should be somewhere here. Right. So that would be the line. Okay, just slightly below it. Yeah, there we go. That should be the line 1.45. And the line 1.2 is the one that's moving vertically upwards there. Okay, and ladies and gents, essentially those are all our points. So it's the intersection between those two. Okay, so let me just remove those. So all we need to do now is just connect those dots together, right? So I'm just going to, right, and there we have it. Okay, I know that it's not the most accurate, but I'm sure you can see that's your graph over there. Right, so ladies and gents, let's look at the next question that follows from that. So they said to us, okay, let's remove this ruler. Okay, they say to us, calculate the gradient of the graph. Now notice, to calculate the gradient, all I'm going to do is just to take our change in y, but remember our y values are acceleration. So change in y, so change in a, divided by change in x, right? But our x in this case is n. Right, notice that's going to be, I can take any between any two values, right? So that would be, okay, let's take this one and the very first one. So that would be 1.45 minus 0.36 divided by, when the acceleration was 1.45, our force was 1.2 minus 0.3. When the acceleration was 0.36, our force was 0.3. Okay, so that's how we'll get the gradient. Okay, you can use your graph to get that gradient. So in that case, what do we have? We've got, okay, 1.45 minus 0.36. This is divided by 1.2 minus 0.3. And I seem to get a value of 1.211111. Okay, I'm just going to say 1.21. Okay, so that's our gradient, right? That's the gradient of the graph. And please note, this is meters per second squared per kilogram, right? So that's meters per second squared per kilogram. And not really that there was a need for me to put my SI units, but nonetheless, it is what it is. Right, and then finally, they say calculate the gradient, or rather use the gradient of the graph calculated in 3.4 to determine the mass of the trolley. Now remember, what is, according to Newton's second law, F net is ma. So if I wanted the mass, it's F net divided by the acceleration. But I want you to note here, what do you have in your gradient? It's actually the other way around. Acceleration divided by the force. So which means that the mass would be the inverse of the gradient, right? Remember, the gradient gave you acceleration over force, but we want force over acceleration. So that means that the mass, that's 3.5, the mass would be 1 over the gradient. Okay, so that would be 1 over the gradient of the graph. So this would be 1 divided by that 1.21. Okay, right, so what I'm going to do, whilst I still have that value there, I'm just going to say shift and I invert that value. Actually, I don't even need to shift it. I'll say the inverse of my answer, and I get a mass of 0.83 kilograms. Right, so that would be the mass of my trolley. All right, I hope that makes sense, guys, as we are going to be moving to the next one. I really took my time on that graph there. And not only do you need to know how to plot the graph, but you need to be able to interpret the graph as well. Right, let's go on to the next question. Right, I hope you will enjoy. Okay, so question 4, they say to us, we've got a tow truck that pulls a car along a gravel road. They say the force applied by the engine of the tow truck is 9,000 newtons. The mass of the tow truck is 1,300, and the mass of the car is 750 kilograms. The vehicles are connected to each other by an inelastic tow bar of negligible mass, and they say see the diagram below. Right, so now what do we have in this case? They say the tow truck and car move at constant velocity. Very important again, remember, we said that when we have constant velocity, we know acceleration is 0. And what that simply means is that the net force will also be equal to 0. Right. Now they say define the term frictional force. So remember that friction is a force that acts parallel to the surface that opposes the motion of an object. Okay. Right, they say name and state the law that explains why the force exerted by the tow truck on the car is the same as the force exerted by the car on the tow truck. So remember, that is Newton's third law. So that's Newton's third law. Okay, and remember, Newton's third law simply states if body A exerts a force on body B, then body B will exert an equal but opposite force on body A. That's the easiest way. Of course, there are other ways to state that law. All right, I will not limit you to what I have said. Right, now they say to us, if the coefficient of friction between the tow truck tires and the road is 0.45, okay, so we know there's friction over there. Okay, and the friction coefficient is 0.45. Right, they say calculate the magnitude of the tension in the tow bar. Okay, so what I'm going to do is I am going to look at the forces that are acting on the tow truck, right? So if I look at the forces acting on the tow truck, so let's first look at all the forces there. So I know I've got the applied force, right? So that's force which is 9,000. But I also have the tension on the string, which is what I'm looking for. But we also have the frictional force, right? So friction. All right. So what are we looking for? We're looking for the tension in the tow truck. But I want you to note, ladies and gents, I have not been able to obtain the value for friction just yet. Okay, but I can do so because I've got my coefficient, and I know that friction, please remember, so friction is coefficient multiplied by the normal force. Now, because my forces are acting horizontally, right, it means that my normal force would be equal to the weight of the truck, okay, of the tow truck. So I hope that makes sense. So what I'm going to do there is I'm going to say, well, F net is equal to ma, but I know that acceleration is 0. So which means I'll have force applied minus the tension minus the friction, okay? And this is, I'm assuming that the direction of motion is positive, and this is equal to 0. So now, this is 9,000 minus that tension minus the coefficient of friction, 0.45, times, so remember we said it's coefficient multiplied by normal force, and I said your normal force should be equal to the weight of the truck. So that's 1,003 times 9.8. 13 times 9.8. Right, and all of that should give us a sum total of 0. So which means what should be our value for the tension? Right, please, if you don't mind, I'm just going to complete it onto this side. So I'm going to say 9,000 minus 0.45 times 1,300 times 9.8. Okay, and I will get a value of T is 3267. So that's 3,267 newtons. And that's my value for the tension on the string. Right, so the next question, they say to us, calculate the coefficient of kinetic friction between the car and the tires on the road surface. Right, now we're going to look at the car. So remember, what are the forces acting on the car? That should be that tension. It should be the friction between the tires and the road, right? But we also do note that it must be that the car is accelerating with 0 acceleration, right? Since it is being pulled by that rope. So I'm going to say, right, so this is going to be sum of forces on the car is equal to 0. That's going to be tension minus the force on the rope. Rather, that's tension minus the frictional force on the car, and this is equal to 0. So coefficient multiplied by the mass of the car, that's 950 times 9.8, okay, is equal to 0. Now note in this case, my tension for the car is exactly the one that we found there, 3267. Okay, so if I take that, 3267, okay, this is equal to coefficient multiplied by 950 times 9.8. Okay, so we divide both sides by 950 times 9.8. What I do on the left, I do on the right. All right, so in that case, what do I get for that coefficient? Okay, so in this case, I will simply have 3267 divided by 950 times 9.8. Okay, and I seem to get a coefficient of 0.35. And please remember that coefficient of friction does not have any units, right? It is a constant. Okay, right, now quickly to go to the last portion. They say to us, suddenly the tow bar between the car and the tow truck disconnect, okay, and the car comes loose. Using relevant law of motion, explain why the car continues moving forward for a short distance. Right, so please remember in this case, this is where we're going to use Newton's law, right? Newton's first law, right? So in this case, what happens to the car? So it will actually, which means the only force now that is acting on the car will be the frictional force, right? They said to us, using relevant equations, laws, explain why the car continues to move forward for a short distance, right? So remember that because friction is the only force that acts now on the car, that means that the car will then begin to slow down, okay, and as a result eventually come to a stop, right? That's as per Newton's second law, right? But also remember Newton's first law or rather inertia, the principle of inertia, right? Why does the car not, just stop immediately, all right? Because remember, according to Newton's first law, a body will accelerate in the direction of the resultant force, right? And in that case, the resultant force, our initial force, was in the forward direction, and so as a result, it will continue in that direction. Okay, right. Without necessarily saying much there, right? So let's go to 4.6. They say calculate the acceleration of the car as it comes to a stop after a short distance. Right. So now remember which force is acting on the car. It will be the frictional force, right? We found out what the coefficient of the of the car is. So now we're looking for the acceleration. So we're going to say F net is equal to ma. The only force acting on the car now is the frictional force. That's coefficient multiplied by the normal force. Okay, and in this case, this is equal to ma. Right, we found our coefficient to be 0.5 times our normal force. That's 950 times 9.8. Right, that's mg. This is equal to the mass, which is 950 multiplied by the acceleration. So we know our frictional force, by the way, is opposing the motion, right? So therefore it should be negative. So let's quickly just get that answer there. So that's 0.35 times 950 times 9.8. Okay, so that will give us divide by, if we say divide by 950, which is the mass of the car. So our acceleration will be negative 3.43 meters per second squared. All right, I hope that we are okay, ladies and gents. That will be how the cookie crumbles. And by the way, I'm not sure why I even bothered, because remember, the frictional force would have been equal to the initial force of on the cable in that case, so which was 3267. Okay, we could have used that right there. All right, so let's go on to the next question, which is question 5. All right, and so we go on to question 5. They say the acceleration due to gravity on planet X is 2.7 meters per second squared, and the radius of this planet is a third of the radius of the Earth. Right, firstly, they say explain the difference between weight and mass. So weight is the measure of the force of attraction that the Earth exerts on a body. And we know that mass is the measure of a body's inertia, or we can say that mass is the measure of matter, okay, of the amount of matter on a substance, okay. Right, so let's go to the next question. They say to us, calculate the mass of planet X. Right, so now what we need to do, ladies and gents, remember, they said to us that, the radius, rather, of the planet, of the mass, rather, they said the radius of planet X is a third of the radius of the Earth. Right, so now, what I'm going to do is, if we were going to measure the weight of this object on the Earth, right, we know that it would be mass times gravitational acceleration. So gravitational acceleration is actually g times the mass of the Earth divided by the radius of the Earth squared, right? Now we know on the Earth it would be 9.8, but on this planet the gravitational acceleration is 2.7, right? So this is going to be 6.7 times 10. And by the way, please remember that you're given all of these constants. That's the universal gravitational constant, just to show you there. So we are given that value for G, that's 6.67 times 10 minus 11, okay? And we are also given the mass of the Earth, right, which is 5.98, and we are also given the radius of the Earth. However, this time around, we are looking for the radius of this planet. Okay, so let's try and look for that quickly. Right, so, okay, there it is there. Right, so they said to us the mass, the radius of this planet is a third the radius of the Earth. So which means this is going to be 6.67 times 10 minus 11 multiplied by, okay, so this is going to be the mass of planet X. So let's say mass of X. And we know that the radius is a third of the radius of the Earth. Right, now please remember, we said the radius of the Earth now, please note 6.64, right? Where is that? I mean 6.38 rather, times 10 to the power 6, okay? So 6.38, so this would be 6.38 times 10 to the power 6, but this is squared. And what we're going to do is just look for the mass of planet X. And what I'm going to do there, if we cross multiply, I know that this multiplies with 2.7 and 6.67 times mx times 1. This is 2.7 over 1. And in this case, we're going to divide. So, and please remember, note that we have squared the amount. So what I'm going to do, I'm going to say, right, this is 2.7 multiplied by, this is 1 over 3 times 6.38 exponent 6. This is squared, all of it squared. Okay, and in this case we're going to take all of that and divide that by 6.67 exponent minus 11. Okay, so that means that the mass of this planet, okay, let's just put it in scientific notation. So the mass of this planet would actually be 1.83 times 10 to the power 23. Okay, and this is kilograms. Okay, right, so that is how we're going to get the mass of planet X. Now, they said to us, determine the factor by which the weight of an object on planet X will differ to the weight of the same object on planet on planet Earth. Right, so the factor by which the weight of the object on X, so weight on X divided by weight on Earth. Now notice the mass would be the same, right? So this is the gravitational acceleration on Earth, on X, and this would be the gravitational acceleration on Earth, right? So what that simply means is that I can take the two gravitational acceleration values, so that's 2.7 divided by 9.8, and so that is the factor. So that's 2.7 divided by 9.8, and that means that the factor is 0. Let's say 28, right? And remember, this is just a ratio, a factor, so there shouldn't be any units in that regard. Right, ladies and gents, that is how we're going to conclude question 5. Let's go on to question 6 now. And now we go on to question 6. They say the experiments are performed to compare the refractive indices of different material. They say in one of the experiments, a light ray passes from air to material A, and the angle of incident and refraction are measured. Right, they say the refractive index of air is 1. Right, so firstly, they give us this graph. They say the graph below was drawn using the results of material A. So firstly, they say to us we must make or give a definition, right, of the term angle of incidence. Right, and please remember, guys, when we talk about the angle of incidence, right, this is the angle between the normal to a refracting surface, right, and the incident ray. So in this case, remember that it would be the angle between the normal. Okay, so remember the normal, right, to, in this case, so that would be the incident ray over there, right? So you are looking at the normal being 90 degrees to the refractive surface, right, and the incident ray. Right, please remember that. So they say calculate the refractive index of material A, right, using the data in the graph. Okay, so what we can do is, of course, we can use Snell's law. All right, so that's the first option. So we can say that if I take from Snell's law and the refractive index multiplied by the sine of the incident ray is equal to the final refractive index, right, multiplied by the sine of the reflected ray. Okay, so in this case, we know that our refractive index for air, they said to us that's 1. Okay, and the refractive index in this case, so that is 1. And so sine of theta I, that's 0.56. Okay, and we want to find out what is the refractive index for the material. sine of theta r is 0.37. Okay, right, so all we simply are going to do is just divide both sides by 0.37, 0.37 rather, and if we cancel that, okay, right, now if you notice there, so if we take our calculator, we'll have 0.56 divided by, so 0.56 divided by 0.37, and I get a value of 1.51. Okay, so that is it there. Okay, so that's the refractive index of the material. What you also could have done is just to take the gradient of the graph, okay, and what then you do with that gradient is that you can take the gradient and say, well, you know that the gradient will be 1 over the refractive index, and so you can find it that way. All right. Now they said to us, calculate the speed of light through the material A. And please remember, ladies and gents, you know, we've got these formulae. So N is equal to C over V, where N is the refractive index, right? So we know this is going to be 1.51. C is the speed of light, so that's 3 times 10 to the power 8. And our V value, this is what we are looking for. And all we simply are going to do is just cross multiply. So V would be 3 times 10 to the power 8 divided by 1.51. Okay, and what do we get there? We'll get 3 exponent 8 divided by 1.51. And that gives me, okay, let's write that in scientific form. That gives us 1.99 times 10 exponent 8 meters per second. All right, and that would be the speed of light through the material A. Right, so the next question, they say, if material A is replaced by material B, the angle of refraction is 31, okay? When the angle of incident is 40, right, they say calculate the refractive index of material B. Right, so once again, we are going to do exactly the same thing, right? So we said this is Ni sine of theta I is equals to Nf, the sine of theta R. Okay, so once again, so we know this is 1 multiplied by the sine of 31. Okay, so that's the angle of refraction. Oh, rather, that's the angle of refraction. So the angle of incident is 40. So that would be sine of 40. And in this case, we're looking for Nf, right, the refractive index, sine of 31. Okay, so let's try and get that. So this would give us, so we're going to have sine of 40 divided by the sine of 31. Okay, and I get 1.25. Okay, so the refractive index in this case will be 1.25. Right, so there we have it right there. And by the way, just to remember, okay, we'll get to that in just a little while. Right, so now they say to us, redraw the graph for material A on the same set of axes, right? And draw the graph you expect from material B. Label the graphs of material A and material B clearly. Now, ladies and gents, what you note there is that the refractive index for material B is actually lower. But remember that this graph here gives me the sine of theta r. You can actually even check it out, right? And say, well, but I know that my angle of refraction in this case is sine of 31. Now let's check, what is sine 31? So if I say sine 31, that gives me 0.51, right? Okay, so that would be my angle of refraction. Okay, so 0.5, so I would have 0.5 there, right? But what would be my incident angle? Okay, that would be 40. So what would be the sine of 40 there? So sine of 40 would be 0.64, right? So in this case, you'd have 0.64, okay, and a much higher value. So you'd have a value over there. So which means the graph B would have a much steeper gradient than graph A. So there are our two graphs. Okay, so this would clearly be graph B. Of course, I already have graph A, but in your case, you would have to draw it. So this is what it would look like. Right, now let's go on to the next part. They say total internal refraction occurs when a light ray passes through the material A to material B. They say the critical angle of material A is 49. Right. Now they say which angle which range of angles will make it possible for total internal refraction. Now note in this case that because our critical angle is 49, then it means that that angle must definitely be less than 90, but it must be greater than 49. Okay, so that is what would cause total would cause total internal refraction. Right, and now they ask us what other condition is necessary for total internal refraction to take place. Right, so we note in this case, now note that we're using material A and material B, right? So which means that the refraction index, right? So the refraction index, okay, for material A, must be greater than the in fact I forgot to say index over there, right? Must be greater than the refractive index fraction index for material B. Okay, so that would be the condition there, all right, in order for total internal reflection to take place. Now, guys, I will still teach this section quite, in depth. Okay, so please look out for that. I will do so in the near future. Right, so let's go to question 7. I hope that question 6 was well understood. Right, so we go on to question 7. So they say to us, an experiment is set up as shown in the diagram below to investigate the effects of slit width, right, and the degree of diffraction. They say distance y on the diagram represents the distance between the screen and the single slit, and distance x on the diagram represents the width of the central bright band. Right, now firstly, they say to us write down an investigative question for this experiment. Now, remember, ladies and gents, what are we trying to find out, right? The relationship between the slit width, right, and the, let's say the distance of the central bright band. okay? Or you can say, in this case, the degree of diffraction. Right, so in this case, they say to us we should write down the investigative question. Right, we can say, how will the slit width affect the angle or the width of the central bright band, right? So remember that an investigative question cannot be answered with a yes or no, or must not be answered with a yes or no, meaning you must you must ask an open question, and please do not forget to have a question mark at the end. Otherwise, then it does not become a question. Right, now they say to us we must state Huygen's principle. Right, so please remember, we say that Huygen's principle simply says every wave of a wavefront, right, serves as a point of a secondary wave that moves forward with the same speed as the wave, right? It is one of those principles that we must know. Okay, right. So let's go to the next question. They say, how will the distance x be affected if the slit width is increased? Choose increase, decrease, or remain the same. Now remember, ladies and gents, that the formula that we use, and I know that it's not given, right? Okay, so this is the formula that we use, right? So in this case, this would be the mth dark band, right? So in this case, because we're looking at the central bright band, our m value is 1, right? This is the wavelength of the source of light that you are using. And now this is the width, the slit width, right? Now, notice, ladies and gents, that it is in the denominator. Now, if we increase the slit width, what happens in this case? It means that we are going to decrease that sine of theta, meaning that our angle will actually get narrower or will get smaller, right? So they said to us, if it is increased, then we know that it will decrease. And they say, explain our answer. We can say that slit width, okay, is inversely proportional right to to the distance, or in this case the measure, we said the width rather, of the central bright band of our central bright band. Okay. All right, ladies and gents. And finally, they say, how will a distance x be affected? Okay, so they want to know about that bright band. If distance y is decreased. All right, now this one goes without saying, ladies and gents. The further away I actually put this, in this case, it means that my diffraction angle would actually be, would increase. So they said choose from increase, decrease, or remain the same. It will definitely increase. Okay, right. So there's not much calculation here, right? So let's go on to question 8. Right, and now let's go on to question 8. They say we've got two identical positive, or rather point charges, x and y, that are placed 2 millimeters apart. Point P is 3 millimeters to the right of charge y. They say the net electric field at point P is 5.44 times 10 to the exponent 6, right, newtons per coulomb. This is to the left. Now, the fact that they told us that P is simply a point. So remember, what we're going to do is we're going to assume, we always do this, we assume that that is a positive point charge, a test charge, right? So we assume that point to be positive. Now, the net electric field at that point is to the left. So which means that we're assuming that that point charge, that positive point charge, would actually be to the left, okay? So meaning that the charges on X and Y respectively have to be negative so that they attract that that point charge to the left, okay? Right, so now they say to us, define the electric field at a point. Remember that electric field, by definition, it is the point where electrostatic force is felt per unit charge, right? Or you can say the area where electrostatic force is felt per unit charge. Right, now they're asking, are the charges negative or positive? We've just stated this, right? We said they should be negative, and the reason for that is that they need to be able to attract that positive test charge. Right, now they say draw the resultant electric field pattern, right, for charges X and Y. Okay, so what I'm going to do there, let me just draw them over here. Okay, these are point charges, right? They are identical in charge. So I know that they are negative, by the way. So that means that our electric field will actually be in that direction. So it will be an electric field that is moving towards the center of the charges. Okay. So let me just try to do this. Okay. Right. So that remember that the fields have to they must not rather cross one another, right? So I'm just trying to draw them so that they are equal or identical. Okay, so there's my charges. Okay, so it was misbehaving at first. Now please remember, because we're dealing with negative charge, we know that the field lines would be moving towards the point charge or inside, okay, towards the center, and that would be the same also for the other point charge as well. Because these charges are equal in charge, right? So that means that the density of the lines, meaning that the number of lines that I will actually indicate there, should be the same. What you can do is just draw that asymptote for yourself there so that you show that they are actually not going to touch each other. Right, so that's what our field line pattern would look like, okay, or our electric field pattern, okay. So they say to us, calculate the magnitude of charge X. Now, remember that you've got the electric field, right, that will be on P because of X and because of Y. So X would be attracting that point charge, so EX, right? But you'd also have EY, and I truly believe, well, not just believe, but I know EY would actually be much bigger, right? Because of the fact that the distance is actually smaller. So, which means E net would be equal to EX plus EY, right? EY. Right, now, our net electric field in this case is 5.44, right? So that's 5.44 times 10 to the raised to the exponent 6, right? And we know this is going to be KQX over. Now, if you notice the distance between X and P, that would be 2 plus that 3. So that gives us 5 millimeters, right? So that would be 5 times 10 negative 3. Note, this is in millimeters, and we must square that distance. Plus, in this case, it would be also KQY, right? And the distance between Y and P is 3 millimeters. So that would be divided by 3 times 10 to the negative 3 squared. Now, ladies and gents, let's just substitute. So this would be 9 times q of x, but we know that q of x is equal to qy, so I'm just going to leave it as q. So this is 9 times 10 power 9q divided by 5 times 10 minus 3 all squared, plus, again, the same thing there. That's q divided by 3 times 10 minus 3 squared. Right, now we're going to try and, so this is equal to 5.44, okay, times 10 to the exponent 6. Right, so we need to find a way in which to add those two together, right? So let's do that. So that's going to be, the first one is 9 exponent 9, okay, divided by 5 exponent negative 3 squared. Okay, so that's the first value for q, plus another 9 exponent 9 divided by, okay, so that would be 3 exponent negative 3. Okay, once again, we're going to square this, and I close that entire bracket, right? So I get 1.65 times 10 to the power 15, and 1.36 rather, times 10 exponent 15 q, when I add both of them, right? And this is equal to 5.44 times 10 exponent 6. So I'm going to divide by 1.36. Okay. Okay, what I do on the left, I do on the right. And what should be our value for q? So this would be, so I'm going to take that answer and divide by 5.44 exponent 6, right? And now what I'm going to do is just simply take the inverse of our answer there. Okay, and what does that give us? That gives us 4 times 10 to the negative 9 coulombs. So this is going to be 4 nanocoulombs, right? But please remember, we did say that they are negative, so that means that we're going to have that negative charge over there, right? But we were just interested in the magnitude, so it's not necessary to put the sign. Right, now they say to us the charge on Y is now replaced with an identical oppositely charged point charge. Okay, so they're telling us that instead of having a negative charge, now we're going to have positive. They say, how will the magnitude of the net electric field at P be affected? It will definitely decrease, right? Okay, so it will definitely decrease. And they say give an answer, give a reason rather for the answer. So notice now what you're going to have is that you're going to have two fields that are opposing each other, right? So it is going to decrease. Okay. Right, and why is that? Because E net is now going to have EY minus EX, whereas initially they were additive. They actually, we took the sum of the two, right? Now, because the other field is now in the opposite direction, right? So the field due to Y, the field on Y will oppose, or rather, let's say, will be in the opposite, will be in the opposite direction. direction. And so the net field, E net, will decrease. Okay, right, so that is really how we're going to answer that. Right, ladies and gents, let's go on to the next section, which is question 9. All right, I hope that was clear. Right, as we look at question 9, they say an induction coil of area 48.6 cubic centimeters and windings, and 200 windings rather, is rotated clockwise in a constant magnetic field of magnitude 2.4 Tesla. They say refer to the diagram below. Right, now they say the graph rather below, shows how the induced EMF varies with the inverse of time. Right, so the first thing is that they ask us to state Faraday's law in words. Right, so remember that, say that the induced EMF, right, is directly proportional to the rate of flow of magnetic flux linkage across them. Okay, so please note that is the formal definition. Right, and then the next question, they say use the information in the graph to calculate the change in magnetic flux. So let's use the formula as we know it. So we've got E, that's minus N over the change in magnetic flux divided by the change in time. Right, now I want you to please note, we can choose any particular point. So I chose to take this point over here. The induced EMF is 3 volts, okay? And they told us that the windings are 200 windings. So that's minus 200, okay? That's change in magnetic flux divided by, now the change in time, ladies and gents, we've got multiplied by, this is 1 over change in time, right? So the corresponding time there, 1 over change in time, is 1.8, okay? So if you look at that, so that increases in 0.2. So that's 1.2, 1.4, 1.6, 1.8, and that becomes 2. So it is at 1.8. That is 1 over time, right? So which means what we are going to do here, you can say, well, 1 over t is 1.8. So which means the time is actually 1 over 1.8. Okay, I hope that makes sense. So let's find out what the change in magnetic flux is. Right, so let's whip out a calculator. We've got 3 times 1 over 1.8. Okay, and we are going to divide that, ladies and gents, by 200. Okay, so I get negative 0.0083. Okay, so remember that is the change in magnetic flux. Okay, and we always use Weber's for that. Okay, right, so that is how we're going to calculate that. Now let's look at the next question. They say that the coil rotates through an angle theta to a position where the magnetic flux becomes 0. Now remember, when does the magnetic flux become 0? When the angle is actually 90, right? So in this case, when the angle between the coil and the field would be 90 degrees, right? So that would be that final point there. And they want us to now calculate the angle theta. Now remember, so that means that the change in magnetic flux would be equal to, the initial flux minus the final one, the final minus the initial rather. Okay, so we know that this should give us minus 0.0083. That's the change that we got. Okay, now how do we calculate the change in magnetic flux, or rather the magnetic flux? So this is going to be B multiplied by the area, right? So this is going to be magnetic field multiplied by the area, right? The cos of the angle. So that's initial minus B times A cos of theta, right? That's for the initial one, and that is the final one. So we know in this case we were given the magnetic field was 2.4, right? So this is going to be 2.4 multiplied by the area is given to us as 448.6, right, cubic centimeters. Now note that finally we said that it will be at 90 degrees. So this will be cos of 90 minus, initially we'll have 2.4 times 48.6, the cos of angle theta, which is the unknown angle that we're looking for. And we know this will give us negative 0.083. Right, now notice, ladies and gents, we know that cos of 90 is 1. Okay, so let's try to deal with that. So we know we're going to deal with this first. Okay, so I'm going to say negative 0.083, 0083, right? Now I'm going to subtract this entire thing. So minus, this is 2.4 times 48.6 cos of 90. Okay. Now notice in this case I get exactly the same. In fact, I just made a mistake. I said cos of 90 is 1, but it actually is 0, right? So that means that becomes 0. So we've got negative 0.083, right? Which is equal to, and it makes sense because remember they said that the magnetic flux becomes 0 there, right? So this is equal to, we've got minus, right? Remember there was that negative sign there, 2.4 times 48.6, the cos of angle theta. So what I'm going to do is I'm going to take all of that and divide by negative 2.4 times 48.6. Okay, and that's the answer that I will get over there, right? And in this case, I want to find out what is the angle theta. So I am going to take that answer and, oh, and by the way, sorry, I made a mistake here. I was supposed to change my, I was supposed to change that to meters, right? So we're supposed to change that to meters cubed. So remember that centimeters, this is 1/100th of a meter. But in this case, we are going to say 48.6, right? But we divide by 100 squared, okay? Because this is centimeter squared, right? Centimeter is divide by 100, and this we're saying divide by 100 squared. Right, so apologies about that. So I'm going to take that and actually have, so that's 0.083, right? Remember this gave us 0. That's minus, now we said that's 2.4 times 48.6 . divided by 100 squared. All right, and this is going to be the cos of theta. Right, so let's do that quickly, ladies and gents. So we're going to have negative 0.08083. Right, this is going to be multiplied by 100 squared there, which gives us 83. Right, and we are going to divide now by that entire thing, which is 2.4 times 48.3. Okay, right, and I forgot the negative there, so I'm supposed to have cos of theta is equal to 0.716 and so on. Right, I'm just going to apologies there, so multiply that whole thing by -1 so that I don't get an answer that is okay. So I'm going to say, right, shift, okay, so my answer, okay, times -1. I see I've made a mistake again. Right, and I'm going to say shift, right, the cos, that's -1. For some reason I'm just failing to get this correctly. Okay, and I'm going to say shift the cos of my answer. Okay, and I get 44.27, ladies and gents. Okay, apologies for those glitches. So this is 44.27, and that would be the angle theta that they asked us to find. All right, I hope that makes sense, and please remember that your area must always be in square meters, right? All right, so that is really how that question ends. Let's go to the last question. And finally, ladies and gents, question 10. So they ask us to look at the circuit. They say the circuit below consists of a 6 ohm and a 15 ohm resistor connected in parallel to an unknown resistor R in series, an emitter, a high resistance voltmeter, a closed switch, and a battery are connected as shown. The resistance of the battery and the wires can be ignored. Right, now let's quickly have a look at it, ladies and gents. So they say the total power dissipated in the parallel part of the circuit is 50 watts. So meaning if we look at those two in parallel, they dissipate a total of 50 watts. Right, now they say define the term power. Remember that we say power is the rate at which work is done. Okay, so now they say to us, calculate the effective resistance of the parallel combination. So we know, so if we want RP, right, I always say, well, you can, if we've got two resistors, it will be product of those resistors divided by the sum. So let's call that R1 and R2. Let's call that R3, right? So it will be R1 times R2 divided by R1 plus R2. So this will be 6 times 15 divided by 6 plus 15. Right, so let's find out. And by the way, nothing wrong if you decided to say 1 over R parallel is 1 over R1 plus 1 over R2. Just remember to invert the answer once you get that. So I am going to say, well, this is 6 times 15. This is divided by 6 plus 15. And so that gives me a resistance of 4.2, okay, let's say 4.29 ohms. Okay, right, so that is the effective resistance of our parallel resistors. Okay, so let's go to the next one. They say calculate the effective resistance rather the potential difference across the resistors in parallel. Now, we know that both these resistors dissipate an amount of 50 watts, right, of power. So I'm going to say, well, for 10.1.3, I know that power is equal to, now note in this case, right, I'm looking for voltage and I have the resistance. So I am going to say power is V squared over R. Please remember you are given those formulae, right? So this is going to be 50. I'm looking for the voltage and I know the resistance was 4.29. Okay, so let's cross multiply. So I'm going to have 50 times 4.29. Okay, and because I'm looking for V, I need to take the square root of that answer. So the square root of our answer will give us 14.65. Right, so that will give us 14.65 volts. Apologies for writing on over that number there. Right, so that's 14.65 volts. Now they say to us, calculate the current through resistor R. Okay, now that we've got the voltage, right, we can find out what the current is, the total current. Okay, so we can say for 10.1.4, that will be V is I times R. Our voltage is 14.65. Right? It will be the total current passing through the combination of both of them. And we know that the resistance is 4.29. Right, so what is that current there? So divide by 4.29 on either one. So that cancels with that. So 14.65 divided by 4.29, and that will give us 3.41 amperes. Right, and that's the total current that's flowing through our circuit. Right, now, and that will be flowing through resistor R, right? That's the total current. Now they say to us, the switch in the circuit is now opened, right? So if we open the switch, so that means that what we will be effectively doing is that once that switch is open, current can no longer pass through this resistor here. We are eliminating the 15 ohm resistor, right? Now they say to us, how will the reading on the voltmeter V be influenced? Choose increase, decrease, or remain the same. Now notice, ladies and gents, that the resistance R, right, of that resistor stays the same. Now, by removing a resistor in parallel, it means that I am actually increasing the resistance of the circuit, right? Now note in this case, so if I increase the resistance, remember the effective resistance was 4.29, but now it will be 6 ohms, right? And so I've increased the resistance of the circuit. What happens to the current? The current will decrease, and that means a lesser current passes through this resistor, and so voltmeter V should decrease. Okay, so our answer there is it will decrease. All right, and they want us to explain that, right? Okay, so firstly, I'm going to say, well, the total resistance of the circuit will increase, okay, when we remove that resistor, right? And so what happens? So the current will decrease. I is equals to V over R. As I increase resistance, current will decrease, right? But now because V is equals to that current times the resistance R, but because R stays constant, remains constant, and I mean the resistance of the resistor, right? The resistance of R stays constant, and so as a result it means that our voltage will also decrease because of a decrease in current. Right, and essentially that is how we're going to explain that, ladies and gents. Right, and finally, they say a geyser labeled 2000 watts is used for an average of 5 hours. Okay, they say the cost of electricity is 80 cents per kilowatt. So that's our rate. So the rate at which we pay for electricity is 80 cents. So that's going to be 0.8 of a rand, right, per kilowatt hour. Okay, now they say to us, calculate the energy used by the geyser for 5 hours per day. Right, so we have got the amount of energy, right? So notice in this case that we've got the power, which is 2000 watts, okay? And we know that power is the rate at which work is done, okay? So power is work done divided by time, right? So the power is 2000 watts, right? We want the energy, and in this case we know it is 5 hours, so that's going to be 5 multiplied by 3600. Okay, right, so in this case that's 3600, which is going to be the total amount of seconds that we have in 5 hours. So energy, right, is 5 times 3600 times 2000. Okay, so we get the amount of energy there, right? So remember, we've got 3600 seconds in 1 hour, but we had 5 hours, so this would be 36 million, right? Yeah, so that would be the amount of energy that we would be using in 5 hours. All right, and then finally, ladies and gents, they want us to calculate the cost of electricity to operate the geyser for a month with 30 days. Right, so now we know that we're going to say the cost is going to be the rate per kilowatt hour multiplied by the amount of energy that is dissipated over that time. Right, so in this case the rate, we said this was 0.8 multiplied by the energy in kilowatt hours, ladies and gents, right? So the energy is 2000 watts, but we need to convert that to kilowatts, right? So 2000 watts is 2 kilowatts. Kilo means 1000. So this would be 2 kilowatts. Okay. But now we need to express the time in hours multiplied by the time, which is 5 hours per day. So this would be 2 kilowatt multiplied by 5, which is in hours. Right, this is the cost per day. So let's do that quickly. That's 0.8 times 2 times 5. So that gives me 8 rands per day. So that would be an amount of 8 rands. But now remember, they said we need to calculate the cost for 30 days. This is per day. Okay. Now for 30 days, all we're going to do is take that amount. Okay. I'm going to say 8 multiplied by 30. Okay. and that will give us 240 rands. Okay, so that's the amount of electricity that we will use in a span of 30 days. Ladies and gents, and that brings us to the end of this question paper. Please remember, you also are given all of those formulae, to use. And please, if you've got any questions, you are more than welcome to throw it in the comment section, and I'll try to answer those questions for you. But of course, if you are struggling with maths and science and you want to get in touch with us so that we can help you out with our services, please go to the description of this video and you'll get all the details that you need. All right, otherwise from me for now, please don't forget to subscribe and like, and please don't forget to also tell others, right, that Malume is still the plug. Otherwise, I'll see you guys next time. Sharp, sharp.